Hello and welcome to lecture 5 of module 7. We have been considering numerical methods for solving ordinary differential equations, the initial value problems in this particular module. So far we have covered the Runge-Kutta family of method, and specifically we have covered RK2 and RK4 methods. In the RK2 method, what we do is we write our yi plus 1 equal to yi plus h times slope, where slope is computed as sum of two slopes k1 and k2. So I will write this as h times w1 k1 plus w2 k2, that is the RK2 method, where k1 is going to be equal to computed as the function f computed at yi comma ti, and k2 is computed at some point yi plus q2 multiplied by h k1 comma ti plus p2 multiplied by h. Okay, q21 multiplied by hk1. This 2 corresponds to this particular 2, the same index, and this 1 index corresponds to this index 1 over here. Okay, so this is an explicit RK2 method that we have over here. Okay, so these weights w1, w2, q21 and p2 are related to each other based on certain rules. Those rules were w1 plus w2 equal to 1, w2 multiplied by q21 equal to half, w2 multiplied by p2 equal to half. These were the three rules that we obtained. We have three equations for 4 unknowns. That means one of those values we can choose on our own, whichever value that we want. Usually we tend to choose our value p2, and based on that we have looked at three different variants of RK2 method: the midpoint method, the Ewan's method, and the Ralston's method. Okay, so this was about RK2, and the way we represent these weights is, what we will do is we will just draw a table with two lines. Okay, and the weights w1 and w2 will go below this particular line, and the weight p2 will come to the left of the vertical line, and q's we will write it in this particular row. So we will have this q21 over here, and we won't have anything in this particular column of the first row. Okay, so this is going to be the representation for RK2. Now the RK4 method, we will have yi plus 1 computed as yi plus w1 k1 plus w2 k2 plus w3 k3 plus w4 k4. Okay, where k1 was as before, k2 was also as before, the same expressions. We may not have the same q21 and p2 values, the expression is the same, it is not the values that are the same. K3 is going to be equal to f of yi plus h multiplied by q31 k1, sorry, q31 k1 this time, plus q32 k2 comma ti plus p3 multiplied by h. Okay, and k4 is f of yi plus h multiplied by q41 k1, q42 k2, q43 k3. Okay. And so now we have our K1, K2, K3 and K4 for our RK4 method, and in RK4 method the same kind of table will have W1, W2, W3 and W4, and then instead of having just one row above this particular guy, we will have 3 rows above this guy, P2, Q21, P3, Q2, Q31 and Q32 and P4, Q31, 41, 42 and 43. Okay. What I will do now is I will go through some of the slides that I have already made to show you some of the variants of the RK4 method. We will just go and review some of the things that we did in the last 5 minutes of the previous lecture, and then we will go on to the RK4 method. Let us start from essentially the overview of this particular module. In the RK family of method, we have considered the RK2 and RK4 as higher order methods. RK3 method is also there, and usually it is RK2, RK3 and RK4 methods that are typically more popular, with RK4 being the most popular, and the reason for that is better accuracy of RK4 method compared to any of the earlier methods. Okay. And the RK2 method I had just written down on the board, and I had gone over these particular expressions in the previous lecture, and we write these the weights in this particular form. Q22 the weight we are not going to use, and so for different values of weights we will get the midpoint method, the Youn's method and the Ralston's method. Okay. Now, when we go to an RKn, we will have a general formulation of this type, where it is a weighted sum of K1, K2 up to Kn, where K1 is the slope computed at y comma t, K2, K3, K4 and so on are the slopes computed at internal points. And we just on the green board we just looked at the expression that we get when n, that is the number of internal points for computing the RK method, was equal to 4. That is, we have seen the RK4 variant on the green board a minute back. Okay. And the table for RK4 method that we get will be constructed in this particular form. So, we have the 4 weights W1, W2, W3 and W4. These are the weights for K1, K2, K3 and K4 to compute the slope S. P2, P3 and P4 are the slopes in computing Ti plus H multiplied by P. These are the P values, and Q values are the weights that are used in computing the intermediate Y points using the RK method. Okay. For example, the classical RK method was P2 was equal to half, P3 was equal to half and P4 was equal to 1. Okay, and Q21 was also equal to half, and then for computing K3 we had used only K2, we had not used K1 at all. So, therefore, Q31 was 0, Q32 was half and P3 was half. So, if you recollect, what we did was we computed the slope at the initial point, then we computed the slope at midpoint. Midpoint means the weights are going to be equal to half. We computed the slopes at midpoints using K1, then we computed the slope again at midpoint not using K1, that is why we get the 0, but using K2 we computed the slope at the midpoint, and that was called our K3, and then using the slope at K3 we projected up to the end point. So, that is why this particular guy is equal to 1, because we are projecting up to end point. That means we are projecting at Ti plus 1 multiplied by H, that is why this guy is 1. We did not use K1 or K2 in this projection, we only used K3 in this projection. So, it was Yi plus H multiplied by K3, and that is why we have this guy equal to 1, and the weights were 1 by 6, 2 by 6, 2 by 6 and 1 by 6. Remember that S we computed as 1/6 multiplied by K1 plus 2 K2 plus 2 K3 plus K4. Okay. So, this is the classical Runge-Kutta 4th order method. Various different people have since devised different methods for computing this or for using this RK4 method. One of the more popular ones, explicit method, is the Runge-Kutta-Gills method, The reason why Runge-Kutta-Gill's method is popular is the objective of the RK-Gill method is not just to minimize the truncation error, but it also tries to minimize the round off error. So with an objective function of minimizing the round off errors, these are basically the weights that are obtained for the RK-Gill method. Perhaps is one of the most popular RK4 methods when it comes to non-adaptive RK4 methods. And finally, we have the Runge-Kutta-Fehlberg method. The Runge-Kutta-Fehlberg method comes under the category of embedded RK methods, and the embedded RK methods I will cover very briefly in the next lecture when I am going to discuss about in the next lecture when I discuss about the adaptive step size methods. Okay, and so these are the weights that are obtained for the Runge-Kutta-Fehlberg method. This is probably the most popular of the RK methods when we are going to use adaptive step size methods using what is known as these types of RK methods. Okay, so essentially what the weights that we get are of this type. We have 1/4 and 1/4 weight for P and Q, and these are the weights for computing K3, and these are the weights for computing K4, and once you get K1, K2, K3 and K4, these are the weights that you will use for W1, W2, W3 and W4. In fact, you can actually indeed verify that sum W1, W2, W3 plus W4 is always going to be equal to 1 in all of the RK4 methods that we obtain. And this particular property, that W1 plus W2 plus W3 plus W4 equal to 1 is required for consistency, and we will talk about that in about 10 minutes from now. Okay. So now to summarize what we get with the RK4 method, what I have done is I have used the solution using the RK4 method using the previous solver that we had developed. Recall that we had developed this particular solver using the RK4 method, and what I did was I changed h equal to 2.5, and for h equal to 2.5 these are the results that we obtained for v equal to 0, v equal to 1, v equal to 0, v equal to 2.5 and v equal to 5. And for v going from v equal to 2.5 to v equal to 5, what I have done is I have just created an animation, and I will just show that animation in the slideshow. Okay. The dashed line that you see, the purple thick dashed line that you see over here is the true solution. The three vertical lines that you see over here are Ti, Ti plus 1 and the midpoint. I have showed the midpoint because in computing the classical RK4 method we are going to use projections at the midpoint. Okay. So we will start at this particular point, okay, and compute K1. So the K1 is computed at the point shown by this black circle. So K1, so the slope K1 is just going to be equal to f of yi comma Ti. Okay. So the slope at this particular point will be K1, and that is shown by the black line over here. Okay. And then we project along this slope up to the midpoint, okay, to compute our K2. Keep in mind the K2 was computed at f of I plus half for time t and I plus K1h by 2 for yi. Okay. So K2 is going to be computed at this point, it is computed at Ti comma yi. Okay. So the K2 computed at this point, these are actual slopes that are obtained from Excel. Okay. This is not a cartoon, these are indeed actual slopes that I have obtained from Excel, and I have animated the slope. So this particular red line that you see over here is the slope K2. Okay. And using the slope K2 we are going to project over here in order to get our K3. K3 again is obtained at the midpoint. Okay. So we take this particular arrow, the slope is unchanged, and we will just bring it back to the point Ti comma yi. and then project it to the midpoint. Okay, so the point ti comma yi is projected at the midpoint, and that we will get as k3, and the k3 is f computed at yi plus k2 h by 2. Okay, so that is this particular point, and ti plus h by 2, which is this vertical point over here. Okay, so now k3 will be computed at this point, and the k3 that is computed at this point is shown by the blue arrow over here. Okay, so this red arrow, the black arrow is k1, this red arrow is k2, this blue arrow is k3. Okay, and the blue arrow gets again moved back to the point yi comma ti, and now what we are going to do is we are going to use k3 to project at ti plus 1. Okay, so we will project along this line all the way up to ti plus 1, and we will compute the slope at that point ti plus 1. Okay, so this is the point at which we will compute our fourth slope, which will be given by this green line. So this is the slope computed at this particular guy, k4 computed at I plus 1 for the time, and I plus h times k3 for the concentration. Okay, so this is the green slope representing k4. Okay, and we take now this green slope back over here. Okay, so now we have k1, k2, k3 and k4. I have discarded all those lines for projections. So 1 multiplied by k1 plus 2 multiplied by k2 plus 2 multiplied by k3 plus 1 multiplied by k4, the entire thing divided by 6 is going to give us the final slope s, and using that final slope we will project up to, from this point we will end up reaching actually a point right over here. Okay, so this is the geometric interpretation of RK4 method using the actual values for the classical RK4 from the Microsoft Excel. Okay, we will do the same thing for Yoon's method also. If we go on to some of the earlier slide, I will just go on to the overview slide. We have covered the Yoon's method under the context of higher order Runge-Kutta method. Now what I will do is I will go on to the predictor-corrector methods, and I will give you a motivation for using the Yoon's method. I will motivate the predictor-corrector method. Okay, so the Yoon's method variant, the RK2 variant of Yoon's method is k1 is the slope computed at this point, and we project all the way up to all the way up to ti plus 1. Okay, so for the k2 will be the slope computed at y plus h times k1 and ti plus 1. Okay, so ti plus h is ti plus 1, yi plus h times k1 is what we will call as y bar. Okay, so the RK2 variant is yi plus 1 equal to yi plus h by 2 multiplied by k1 plus k2. Okay, now what we can say about k1 is that k1 predicts what value we will reach with yi plus 1. So this y bar I plus 1 is the predicted value yi plus 1. Okay, so what we are going to say in the predictor-corrector form is, instead of calling this as yi plus 1 equal to yi plus h by 2 times k1 plus k2, we will call this as yi plus 1 equal to yi plus h by 2 times f of yi plus comma ti plus f of y bar I plus 1 ti plus 1. Okay, where y bar is the predicted value yi plus h times k1. Okay, so this is the predictor-corrector variant. Now let us put the Yoon's method in the predictor-corrector form. Okay, so k1 is the slope computed over here, yi plus 1 bar 0 is the predicted point at this particular location. Okay, and now we write the corrector equations. The corrector equation is k2 0 is going to be nothing but f at yi plus 1 bar 0 comma ti plus 1. Okay, and the new value y bar I plus 1 computed using the first iteration is going to be yi plus h by 2 multiplied by k1 plus k2. Okay. So, if we stop at this location, what we are going to get is we are going to have these two slopes, this black slope and this red slope, and the new slope is going to be just an average of this slope using the Yoon's method. Okay. If we stop at this point, we will get a predictor-corrector form of Yoon's method, which is exactly the same as the RK2 method. Okay. But there is no need to stop at this point. Okay. This is going to be the average of the two slopes. The average of the red line over here and the black line over here is shown by this particular thin line. Okay. Now, this thin line we can use to project once again to get y bar I plus 1 2. Okay. This y bar I plus 1 1, in the same manner we can get y bar I plus 1 2, which is essentially going to be this point. Keep in mind k2m is just going to be nothing but this particular slope, which is midpoint of the previous slopes, and now we compute the slope at this point. We project it back, that the slope computed at this point, discard the red lines which represent the corrector forms for the first iteration. Okay. So, now we have the corrector form for the second iteration. Now, we have this black line and this blue line, and we can get the average of the black and blue line, and we can keep repeating this again and again multiple number of times in order to get the Yoon's method, the predictor-corrector form. Okay. So, what I have done is I have shown you the Yoon's method in the predictor-corrector form using animation, using Microsoft Excel results. Now, what I will do is I will go on to the green board and I will again rederive the Yoon's method using the predictor-corrector form. Okay. So, now let us on the green board, let us say the RK2 variant of Yoon's method and then the predictor-corrector variant of Yoon's method. The general RK2 method I had already written down on the board. So, for Yoon's method, the weights W1 and W2 are 1 by 2 and 1 by 2. So, I will replace them by those numbers. So, I will replace W1 and W2 by half each, and I will take half outside the bracket. So, we will get this as h by 2. K1 was nothing but f computed at yi comma ti, and K2 is f computed at yi plus 1 multiplied by hk1. Okay, that was what Yoon's method was. Our q21 and our p2 were both equal to 1. So, I will write it in that particular form. So, it is h multiplied by k1 and ti plus h over here. Okay. So, this is going to be our k2. Okay. So, now what we do is we call this particular guy, we call this as a predicted value. We will call this predicted value y bar I plus 1 0. Okay. And this predicted value we will correct it using Yoon's method recursively. Okay. So, that is what we are going to do with this. Okay. So, now if we were to use this RK2 variant, this is where we stop and we do not proceed ahead any further. This becomes the RK2 variant, which is equivalent to the Yoon's method predictor-corrector with the corrector used once only. Okay. Now, the predictor-corrector form of Yoon's method, where we use the corrector multiple times, is what I am going to write now. Okay. So, the Yoon's method with the predictor-corrector form, again we will write down the same expressions, pretty much we will derive the same expressions in the same form. First thing to do is to derive the predicted value. So, first item in our agenda is to choose the predictor which uses the value k1 only. So, our predicted value y I plus 1 bar 0 is going to be equal to y I plus h multiplied by f of y I comma t I. Okay. So, if we look at what our y I bar 0 was, if we go back to this particular part and see what our y I bar 0 was, our y I bar 0 was nothing but y I plus h times k1, k1 was nothing but f of y I comma t I. Okay. That is the predictor. So, that is the same equation that I have written in a slightly different form over here. Okay. Now, let us look at the corrector form of the equation. Okay. Corrector was nothing but a trapezoidal rule that we use. 2 lectures earlier, I believe in lecture 3 we had shown that the Yoon's method is kind of like using a trapezoidal rule if we had the function f as function just of the time t. Okay. Likewise, the corrector form is going to be the implementation of trapezoidal rule. In the corrector form, what we do is y I plus 1 corrected, we will write this equal to y I plus h by 2 multiplied by k1 plus k2, right. We have this as k in computing the Yoon's method using RK2, we have y I plus 1 equal to y I plus h by 2 multiplied by k1 plus k2. What is k1? K1 is nothing but the slope computed at y I t I. What is k2? K2 is nothing but slope computed at y I plus 1 bar 0 and t I plus 1. Okay. So, I will write that down over here. So, h by 2 multiplied by f of y I comma t I plus f at y I plus 1 bar 0 comma t I plus 1. Okay. Now, if we stop at this point, the result that we get from the Yoon's predictor-corrector method is the same as the result that we will get from the RK2 method, but we are not going to stop at this point, but we are going to use the corrector multiple number of times. Okay. So, the third item is the multiple use of corrector. Okay. So, what do you mean by multiple use of corrector? Instead of calling this as just y I plus 1 corrected, I will just erase this corrected part. I will put a bar over here and write this as y bar I plus 1 superscript 1. Okay. So, the multiple uses of corrector would be y I plus 1 bar 2 is going to be equal to y I plus h by 2 multiplied by f of y I comma t I plus f of y I plus 1 bar 1 comma t I plus 1. Okay. So, if we compare it with the first use of corrector, if we compare the second use of corrector, instead of computing y I plus 1 bar 1, we are now computing y I plus 1 bar 2. Okay. This guy remains the same. Okay. This particular guy does not change. What it means? It means it is the slope that is computed at the initial point. Okay. So, this means it is a slope computed over here. Okay. Y bar 0 is going to be y bar I plus 1 0 is going to be the point that is projected using this particular slope. Okay. So, y bar 0 is going to be the yellow line that. So, y bar 0 is the point by the yellow x. Okay. And f of y bar 0 is going to be the yellow arrow over here. Okay. So, now what what we do with this particular guy is that we project again using the average slope of y bar 1 and yi. So that means we are going to use this yellow slope and this white slope, and then we will get this, the average slope is going to lie midway between these two arrows, okay, and that is going to be this particular dotted line, okay. So our x over here is, or the star over here is going to be this particular guy over there, okay, and the slope computed at that point is, I am going to show this with a red arrow, okay, and that red arrow is going to be the slope computed over here, and that red arrow is this particular guy, okay. So then I will draw this red arrow over here. I will now discard these yellow arrows. I do not really need these yellow arrows anymore. So okay, I will just discard these yellow arrows, get an average slope of this white and this red arrow, and that average slope I am going to predict once again to the end, and this is our purple x. Our purple x is over here. Now I can use, so this is the second time I have used the corrector. I will use the corrector third time, fourth time, and so on and so forth. I will use it recursively in order to get better and better guesses, okay. So the recursive use of this corrector means that this guy has to be replaced by appropriate quantity, okay. So we will replace this with m plus 1, okay, equal to yi plus h by 2 f yi ti plus f of yi bar m instead of 1 comma ti, where y0 is obtained from this particular equation, and this equation is used for m equal to 0 to some capital M, okay. So we use this predictor, the corrector equation a capital M number of times. We pre-decide what this M is going to be. So let us say that we are going to use the corrector equation 5 times. So we will use the predictor equation once, we will use y0 in order to compute y bar 1, y bar 1 we will use to compute y bar 2, y bar 2 to y bar 3, y bar 3 to y bar 4, and y bar 4 to compute y bar 5, okay. When we reach y bar 5, that is when we say that the solution is the solution that we need for t I plus 1, and the entire process is repeated all over again at the next step, okay. So that is the idea behind predictor corrector methods. We will take up predictor corrector methods once again in the last lecture of this module, when I very briefly am going to cover some of the more advanced methods and why this idea of predictor corrector method actually is fairly popular in some of these methods, specifically in the Adam-Moulton family of methods. Those are also the predictor corrector methods, okay. So in summary, what we have covered so far is we have covered RK methods, we have covered the error analysis of RK methods, and we have covered the predictor corrector methods. The error analysis of the predictor corrector methods is fairly straightforward. This is nothing but an Euler's explicit method. As a result, the error for the predictor equation is that its order of h squared. Okay, whereas the corrector equation is kind of like using the trapezoidal method, and because it is kind of like using the trapezoidal method, the error in corrector equation is of the order of h cubed, okay. So this error is of the order of h cubed, this error is of the order of h squared. Now why is this particular method actually useful? The reason why predictor corrector methods are useful is because they are still explicit methods, they are not implicit method, but if this Yoon's method was repeated large enough number of times, in that case what will happen is that if there is convergence, then Yoon's method will converge to a totally an implicit method. Okay. Why that is so is what I mean by that is every time what we do is when we use this particular equation y bar m plus 1 is changing compared to y bar m plus m. Okay. So if we go from y bar 0 to y bar 1 and so on up to say y bar m, and we go to y bar m plus 1, okay, if the error between y bar m and y bar m plus 1 is very small, okay, if that error is very small, then if we are going to substitute that in this particular equation, the equation that we are going to get is y bar m plus 1 is going to be equal to yi plus h by 2 multiplied by f of yi comma ti plus f of y bar m I plus 1 comma t I plus 1. If m is large enough, okay, we repeat this multiple number of times till we get convergence. If m okay, if m is large enough for convergence, then what we are saying is y bar m plus 1 is approximately equal to y bar m, okay, and let us just represent this as ym, or let us just represent this as y bar without any superscript over here, okay. So if we write y bar m plus 1 equal to y bar and y bar m also equal to y bar, we will get our y bar computed at time I plus 1 equal to yi plus h by 2 multiplied by f of yi comma ti plus f of yi plus 1 bar comma ti, okay. Keep in mind that this bar just represents a dummy type of variable. Now if you see this particular equation, this equation is, if you recollect something that we did in lecture 2 of this particular module, this is nothing but Crank-Nicholson method. Okay, and this completes the promise that I made in lecture 2 itself, why Crank-Nicholson method is going to be preferred over implicit Euler method. The reason why Crank-Nicholson method is going to be preferred over implicit Euler method is because implicit Euler method we saw was of the order of h square accurate, and we have just derived that because of this corrector equation, a method of the type of Crank-Nicholson method is h cubed accurate, okay. So to recollect what we have done in the last half an hour, we started with RK2 method, okay. Specifically we started with the Yoon's variant of the RK2 method. From the RK2 method we said that by repeatedly calculating this guy K2, okay, what we are going to do is we are going to convert that RK2 method into a predictor-corrector Yoon's method, okay. In the Yoon's method we use this predictor equation, that means we use K1 as a predictor equation, okay, and then use the K2 equation repeatedly in order to improve or in order to correct the value of y bar. We go from y bar 0 to y bar 1 and so on up to y bar capital M, okay. So this is what we do in order to use the predictor-corrector Yoon's method. Now instead of stopping at capital M number of iterations, if we keep doing the iterations until y bar m plus 1 converges to y bar m, okay, then what we have solved over here is we have essentially solved a non-linear equation of this type. We have solved this equation using the fixed point iteration method, the method of successive evaluations, okay. So if we actually do that, we will get Crank-Nicholson method, okay. If we stop at a finite number of iterations, we will get the predictor-corrector method. If we stop only in the first step, not do any iterations of the corrector, we will get the RK2 Youn's method, okay. So that is basically what I wanted to cover with respect to RK2 methods and with respect to the predictor-corrector methods. The next question and a very important question comes up is, why do we want to look at the implicit methods at the on the first in the first case itself? Because the RK2 method we saw had accuracy of h cubed, predictor-corrector had an accuracy of h cubed, Crank-Nicholson method has an accuracy of h cubed, but clearly the amount of effort that is required in order to solve this particular algebraic equation problem is significantly higher than the amount of effort that is required to solve the RK2 method. So the question comes is, why implicit method, and the answer to that question is because implicit methods are more stable. Okay. The question is, what do we mean by stability? Okay. So let us again go back to the Microsoft Excel and try to see what we actually mean by stability. So now let us consider what we mean by stability. What I have done over here is from the same Excel sheet that we have been looking at in the past few lectures, I have opened up the same Euler's explicit method sheet, okay. So this is where we computed the where we used Euler's explicit method in order to compute the solution for V equal to 5, given that concentration C0 equal to 1, okay. What we had seen is, as we decrease the value of our step size h, we get more and more accurate results. Likewise, as we increase the value of our step size, we are going to get less and less accurate results. So from h equal to 1, let me increase this to h equal to 1.5, okay. What happens when we increase this to h equal to 1.5? What I will do is I will just take this figure a little bit away so that it does not distract us from our discussion, okay. So what happens when we go from h equal to 1 to h equal to 1.5 is that the error that we get increases, okay, but nothing more has happened besides error increasing, okay. Let us go to h equal to 1.8 and again we find that the error has increased even further. Let us now go to h equal to 2, okay. Now when we see h equal to 2, there is some funny business that is happening, okay. That if you look at the predictions of the Euler's method with h equal to 2, the initial concentration was equal to 1, but the concentration immediately at volume V equal to 2 has dropped to 0, okay. And beyond that, this method cannot continue because C itself is 0. When C is 0, f that is computed is 0. If f that is computed is 0, then Ci plus 1 equal to C plus h multiplied by f is going to be equal to Ci itself. So Ci plus 1 equal to Ci equal to 0. So immediately within one step, Ci has gone to a value equal to 0, okay. So now that is a little bit of a problem over here. This problem arises because at h equal to 2 we have limit of stability of this particular method. What that means is, let us go from h equal to 2 to h equal to 2.1, okay. And if we go to h equal to 2 to h equal to 2.1, this is what we observe. What we observe is quite clearly that the concentration goes to a negative value, and beyond that our method cannot proceed. Okay. The reason why the method cannot proceed is because the concentration to the power 1.25, it is a fractional power. As a result of the fractional power, because we get negative concentration, we are not able to proceed further. Okay. So now what I will do is I will change this problem a little bit from dc by dv equal to 1.25 to dc by dv equal to minus c to the power 1 divided by 2. Okay. And what we will do is we will go back to h equal to 0.5. Okay. And let us see what happens. Now let us consider the case where we have f to the power 1 instead of f to the power 1.25. Everything else remains the same. I have only changed this particular expression over here. Okay. So now I will drag it and drop it over here, and the true values are also going to change. True values are going to be for the first order reaction, basically the true values are going to be e to the power minus t by 2. Or e into minus 2t. Okay. Okay. So with this particular change, okay, what we have is dc by dv dc by dv is going to be equal to minus 0.5 into c. Okay. So what we can do is dc, we can write this as dc divided by c is going to be equal to minus 0.5 into dv. Okay. And when we integrate this, we are going to get ln of c equal to minus 0.5 into v, integrating from 0 to v and from ca0 to ca. So we will have ln of c divided by ca0, where ca0 was equal to 1. So ln of c by c is going to be equal to minus 0.5 v, or c is going to be e to the power minus 0.5 v. Okay. And this is what we have written over here. Concentration is equal to e to the power minus 0.5 multiplied by v, or minus v divided by 2. Okay. So that is the true value that we get. Okay. The numerical value using Euler's explicit method for h equal to 0.5 are as shown over here, and we can extend it further. Okay. And we can extend it up to v equal to 5, and we will get the concentration of the species coming out from the PFR using the Euler's explicit method. Now let us increase our h to 1 and see what happens. When our h has increased to 1, the overall errors have also increased. Okay. So the errors have increased indeed when we go from h equal to 0.5 to h equal to 1, but the solution is still available for us to see. Now if we go from h equal to 1 to h equal to 2, what happens is what we had seen earlier. Immediately the concentration has become 0, and from that point onwards we cannot proceed. Okay. Now what do we do if h happens to be h equal to 2.1, and this is what we see when h equal to 2.1 is that the concentration has become 1, it has become negative, and then it is oscillating and finally settling down at the steady state value. Okay. Now let us say if h equal to 4, what happens? We get the value oscillating at 1, minus 1, 1, minus 1, 1, minus 1 and so on. Now if h is increased to 5, there is an interesting thing that happens. It is 1, minus 1.5, 2, minus 3, 5, minus 7, and now when I increase h to 10, see what is happening is see 1, minus 4, 16, minus 64, 256, 1024. Okay. So what essentially is happening over here is as we are increasing h beyond a certain point, the solution from Euler's method is going unstable. So I will go to the green board and I will plot out what actually happened in the Euler's explicit method. Okay. Okay. So what I have said over here is implicit methods are more stable. We are investigating what it means by stability. Okay. So what happened, what we saw over here is if we were to plot the concentration C against the volume, okay, the numerical method for getting concentration C against the volume, if we were to use say h equal to 1, we will perhaps get the results something like this. Okay. If we were to use h equal to 2, okay, we will get perhaps the result going something like this. Okay. When we used value h equal to 2.1, the results that we got were something of this sort. This is when h, again this is a cartoon, so this is not exactly drawn to scale, this is just to show you what we get. Now when h was equal to 4, the type of results that we got when h was equal to 4 okay. So this we started out at 1, this value was minus 1, this value again was 1, this value was minus 1, this was 1 and this value was minus 1 again. Okay. So this is the curve that we got when h was equal to 4. Now what do we get when h is increased to beyond 4? What we get when h is increased to beyond 4 is this particular value goes beyond minus 1, the next value goes beyond 1, the value after that goes even below minus 1, so on and so forth. So if we were to shrink this plot, if we were to shrink the ordinate for this particular system and we were to plot this, okay, for h greater than 4 we will start at minus 1, sorry, we will start at plus 1, go to a value below minus 1, okay, and if we repeat it for large enough volume, what we will get is we will get the overall result oscillating between minus infinity and plus infinity as v tends to infinity. This is known as an unstable solution. Okay. So I am going to end the lecture over here in this the lecture 5 of this module. I am going to end over here. In the next lecture I am going to consider the stability issues. Okay. Specifically I will talk about the equation. So the equation that we had dc by dv was equal to minus c by 2. Okay. For this particular condition we saw that when h becomes greater than 4, at that time the explicit Euler's method becomes unstable. Okay. And we will do some theoretical analysis of this particular condition to find out under what conditions do the explicit Euler method becomes unstable, under what conditions do implicit Euler methods become unstable. And what we will show is that implicit methods are globally stable, there is no limit on h for which this remains unstable. What we will also show is that the condition for which explicit Euler's method becomes stable is going to be when h is greater than 2 divided by the coefficient of this term. Okay. When that h is greater than 2 divided by 1 by 2, that is when the explicit Euler's method is going to be unstable. That is something that we are going to start off in the next lecture in this particular module. Okay. Thank you.